This is the introductory lecture to Chapter 17, all about chemical thermodynamics. And you may not remember, but in the first semester of Gen Chem, there was a brief chapter on thermochemistry. So this is kind of upper level thermochemistry. And rather than simply talking about exothermic and endothermic, we're going to go into what determines whether or not a process is spontaneous and something called Gibbs free energy. So this is the introductory lecture, and I'm going to start out with a brief definition for you of thermodynamics, and it's basically the study of energy changes that accompany chemical reactions. And I think the biggest difference you're going to notice in this chapter is the introduction of the term entropy, spontaneity, and Gibbs free energy. We'll start off discussing the first two laws of thermodynamics. The first law of thermodynamics, which you're probably really familiar with, is that energy can neither be created nor destroyed. The amount of energy in our universe is constant. Throughout this chapter, we'll be talking about the system and the surroundings. The system is actually the molecules, the chemical reaction, or the process that we're studying. The surroundings is everything else around it. In this picture, it would be the cylinder and the piston, all the air around it, anything but the molecules we're studying. And the reason they do that in thermodynamics is you can't really get, for example, a thermometer or something in the middle of molecules and study exactly what the molecules are doing. So what we usually study in chemistry are the surroundings, and then we kind of reverse all the measurements we get. So if our surroundings are getting hot, that means that the system itself is giving off heat and itself is cooling. So anyway, remember those two terms, system and surroundings. Now, the second law of thermodynamics you may not be as familiar with. You've probably heard it mentioned or seen it mentioned as that the entropy of the universe is always increasing. But I don't know that that has a lot of meaning to most of us. So let me talk about that a little bit. First of all, what is entropy? A lot of textbooks will call it a state of disorder, a state of randomness. Pure physicists don't really like those definitions, and I don't really like them either. So what entropy really is the spreading out of energy or the dispersal of energy. Why do we even care? Because when energy gets spread out or dispersed, it's not as useful. For example, I'll explain what I have in this paragraph, but then it's there for you to read also. Let's think of a power plant delivering electricity to our homes through the wires. That delivery is not 100% perfect. Quite a bit of that energy that's delivered in those wires is lost through heat. And that's the second law of thermodynamics. That's because of entropy. Even the energy, the electrical energy that reaches our home and that is used to light our lights or run our washer and dryer, ultimately that energy, even though we use a good part of it, the energy still gets spread out in large part, again, because of heat, gets converted into heat. And eventually, all of the used energy will disperse into space and not be useful anymore. So that is the second law, is that entropy of the universe is always increasing. And that is why we worry about how much energy we have. We talk about running out of oil and things like that, and look to solar energy that's renewable. And if you ever think about it, why should we worry about energy if the first law of thermodynamics says that the amount of energy is constant? Where's it going? Why do we worry about it if it's constant? Because even though the total amount of energy is constant, it's becoming less and less useful because the entropy of the universe is increasing. So that's just a concept that I want you to understand. The second law of thermodynamics explains a lot of things. For example, it explains why energy in the form of heat always moves from a higher temperature, to a lower temperature. And that's because the heat, the energy, okay, heat is just the flow of energy, it spreads out more when it moves from a higher temperature to a lower temperature. So when you open your door in the middle of winter, it's not the cold coming in, it's the heat rushing out. And again, that's entropy increasing. Why do we really care about all this? Why do chemists care about it? Because things like entropy and enthalpy tell us whether a process or chemical reaction will occur spontaneously. What do I mean by spontaneous? That a process will occur on its own without any outside intervention. Okay? Non-spontaneous processes can be made to go, but something or somebody needs to come in and give them a boot, more energy. I do want to emphasize at this point that spontaneity has absolutely nothing to do with the speed of a reaction. Something can be spontaneous and slow as heck, okay? For example, rust. The process of rusting is a spontaneous process. It occurs without any outside intervention under the conditions of being outside and the weather and rain. That's normal conditions. But it occurs very, very slowly over a period of years. So that's just to emphasize to you that spontaneity has nothing to do with speed of a process. And I also want to make a point at this time that if a process is spontaneous in the forward direction, it will always be non-spontaneous in the reverse direction. And we'll look at the energetics of that later. Wouldn't it be nice if we could somehow make rust turn back into metal? Now, in this introductory lecture, I'm touching on a bunch of misconceptions that I've noticed students get. And I've begun to kind of emphasize to you that spontaneity has nothing to do with speed. So let me show you a typical energy profile for a chemical reaction or a process. And in these graphs, which you need to be able to interpret, energy is typically on the y-axis, and the reaction progress is on the x-axis. So, of course, our reactants would be on the left side and the products on the right side. And we love energy profiles because they tell us the relative energy of the reactants and products. And, of course, normally when you've looked at this before, you've said, okay, for example, this graph shows the products have a higher energy. And so you would normally say, okay, well, this reaction is endothermic, which means heat or energy has to be absorbed by the reactants in order to get to the products. So the bottom part of the graph is where thermodynamics look. That tells you spontaneity, tells you about enthalpy, entropy, free energy, which you haven't learned about yet. And the top part of the graph tells you about kinetics, the rate of reaction, okay? This, if you remember from our kinetics chapter, is the activation energy. So they're relatively unrelated to each other. I mean, there are some relationships, but not direct. So for this chapter, we'll be looking down here at just the energies of the reactants and products, not the rates of reactions and activation energy. So let's talk about spontaneity a bit. You know from what we've learned before that there are some processes that are exothermic, which means that they release energy, right, in the form of heat. And we know that that's favorable, okay? And so you might jump to the conclusion that exothermic reactions are spontaneous. And actually most of them are, but not all of them. There are actually some spontaneous processes that are endothermic, that require absorption of energy. So, how is it possible if we have an endothermic reaction for it to go spontaneously? Because spontaneous means without outside intervention. So there's got to be a piece of the puzzle that we're missing, okay? If we have endothermic reactions that occur spontaneously without outside intervention, Where's that extra energy coming from? That's where entropy comes in. And this is a new concept which you're probably going to really need to pay attention to. Let me first give you a couple of examples of processes that are endothermic. They require absorption of energy, but they're still spontaneous. Let's imagine taking an ice cube out of the freezer and laying it on your kitchen counter. It's going to melt spontaneously, okay? No outside intervention if you lay it on the counter, okay? It's going to melt spontaneously. So, but we know it's endothermic. We know the melting process itself requires absorption of energy, so that's not driving it. The endothermic part is not favorable. So what is favorable? It turns out that the entropy of the melting process is very favorable. Okay? So let's talk a bit more about what entropy is. Entropy, one way to think of entropy, I told you it was a dispersal or spreading out of energy. But when we're trying to decide if a process has favorable entropy or not, it's easier to think of entropy as the freedom of motion within the system. The more freedom of motion something has, the more entropy it has. So now let's look at these little particles of ice in the solid state. They're packed very tightly. They can only vibrate. They don't have much freedom. When they melt and become a liquid, there's more space, they have more freedom of motion, and therefore the entropy of the liquid is higher than that of the solid. There's more freedom. That's a form of energy. When entropy increases, that's a form of energy that is favorable. And so the entropy is favorable enough in the melting process of ice that it occurs spontaneously. Let's look at another example. It's another phase change. Water evaporating. Water doesn't just evaporate suddenly, but if you spill some water on your counter and go away for a few hours and come back, some of it's going to be evaporated, which means that the evaporation of the water is spontaneous under the conditions of your kitchen. And so again, evaporation, we know, is an endothermic process. It requires absorption energy, and that means delta H, which is the enthalpy, has a positive sign. Remember, things that are unfavorable, the enthalpy has a positive sign. And so that's not the driving force for evaporation. What is again the increasing entropy. So we discussed in the previous slide going from a solid to a liquid has favorable entropy. Entropy is increasing. And now we've learned from this slide that going from a liquid to a gas, that's more freedom of motion. There's more freedom of motion here in the gas stage. So that also has increasing entropy. Here's a spontaneous process that is also driven by entropy, but does not involve a phase change. So if you put something soluble in water, that means that's a spontaneous process, right? The term soluble implies that it's a spontaneous process. If you put salt in water, and some of it's going to dissolve spontaneously. Why is that? It's because the freedom of motion, you look at the solid crystals, they're very tightly packed. The entropy of this solid is very low. Okay, entropy of all solids is low, but especially an ionic crystal. When you dissolve a compound in water, there's a lot more freedom of motion, and the entropy increases quite a bit. So change in entropy is favorable for dissolving also. So to summarize, when we see increasing entropy, so higher entropy, I want to make a note to you, means favorable. That's a good, this not let me write. Okay, so higher entropy is a favorable process. More freedom of motion is energetically favorable. So just to summarize, entropy becomes more favorable or increases when a solid becomes a liquid or when a liquid becomes a gas. Entropy also increases when a solute dissolves in a solvent. And entropy also increases as temperature increases. As you can imagine, when you increase the temperature of something, you've got more freedom of motion, and therefore the entropy goes up. To summarize what we've learned in this introductory lecture to Chapter 17, Thermodynamics, we have talked mainly about spontaneity. We have learned that there are two factors involved in spontaneity. They are the enthalpy of a process, and let me just remind you that enthalpy, and we'll talk more in detail about it in the next lecture, is represented by a symbol delta H, so enthalpy change, and that has to do with heat changes, exothermic and endothermic, and then there is entropy change that we also want to be aware of now to predict spontaneity. The symbol for entropy, and again we'll go over it more in the next lecture, is S, okay? That has to do with the freedom of motion. The last thing I want to mention in this introductory lecture is that when enthalpy of a process is favorable, the mathematical sign will be a negative. This is what I'm getting ready to say is unusual, so please pay attention and make note of it. When the entropy change for a process is favorable, the mathematical sign that you're looking for is positive. Okay, so they're kind of different from a mathematical. And that brings me to a warning. The most common student mistakes in thermodynamics is mixing up the mathematical signs. As you can imagine, once we put values, numerical values to these and do calculations, if you mess up your plus and minus sign, you're going to get the wrong answer. So be aware of that. That's it for this first lecture.